The sequence diagram and state diagram serve as functional and behavioral maps for the derivation sheet, translating its abstract proofs into a clear timeline of events and a set of real-world scenarios. While the derivation sheet provides the formal rules, these diagrams explain the operational logic and the geometric consequences of those rules without the need for complex formulas. The sequence diagram. An operational roadmap. The sequence diagram organizes the logical steps of the derivation sheet into a chronological timeline, showing exactly how a vector is built and measured. Mapping the construction. It mirrors the part of the derivation sheet where a vector is first defined by its building blocks. It labels the tangent basis as a construction crew, showing that the physical assembly of the vector must happen before any measurement can take place. Visualizing the sieve. The diagram brings the sifting property of the derivation to life. It illustrates how the dual basis acts as a mathematical filter or directional sieve, designed to be blind to the wrong building blocks so it can isolate the exact component needed. Confirming stability. It reinforces the final conclusion of the derivation by showing that even if the system moves, this sequence ensures the resulting measurements remain constant and reliable. The state diagram. A behavioral stress test. The state diagram validates the derivation sheet by illustrating how the system behaves under different geometric conditions, ranging from a perfect setup to a highly distorted one. The baseline state. This matches the standard examples in the derivation sheet, establishing the dual basis as the correct measuring stick for systems where the building blocks are not at right angles to each other. The compensation effect. The diagram illustrates the nearly parallel section of the derivation, showing that the system's rules still hold even when the coordinate system is squashed. It provides a stability intuition that is often missing from static math. As the building blocks close in on each other, the measuring tools must stretch significantly and rotate outward to maintain accuracy. Conservation of orthogonality. The animation state in the diagram proves the dynamic invariance of the derivation. It shows that as the geometry shifts in real time, the system dynamically adjusts to ensure the relationship between the building blocks and the measuring tools is always preserved. In short, the sequence diagram teaches you the order of operations: build, filter, extract, while the state diagram teaches you the system's limits and sensitivity: normal, distorted, dynamic. Together, they ensure that the mathematical proof found in the derivation sheet is grounded in a clear, visible reality.